we proceed through the inductive journey, we're going to be skipping certain topics. In this video, I'll explain why I'm skipping these topics, and I will explain what the implications for these skips mean for the inductive rigor of this inductive narrative. So first of all, I'm going to let you know that I'm going to be skipping decimals. I'm going to be skipping the introduction of decimals, the arithmetic of decimals, and I'll tell you why later. I'm also going to be skipping things like the flip and multiply rule when dividing fractions. You'll notice that the method of dividing fractions that I induced in the last inductive video is not the modern method we use. And the reason for that is that I couldn't find the specific motivation required to develop that method. Even though that method is, of course, superior to the method that I induced, I was unable to show the prior inductive evidence that would have led people towards that more advanced modern method. Now, future inductions are going to be skipping more things, and these skips are conducive to the future goals of the inductive physics project, and let me explain why. So first of all, let me remind you, what are the goals of the inductive physics project? Well, in this context, there are two goals that are worth noting. First, the goal is to demonstrate the inductive method. Demonstrate how, if you lay out observations and reasoning steps in the right order, citing specific methods, then you are able to come to the conclusions with certainty. Second, our purpose is to demonstrate the power of the inductive method by using it to discover new principles of physics. Now, in this journey, using the method to discover something new is way more important than perfectly developing a rigorous reproof of everything. The reason for this is that most people are not convinced of the power of induction. This is one of the battles I'm fighting, is showing that this is actually necessary, to show that some good actually comes from reproving everything. A lot of people, like a lot of scientists, aren't even sold on the idea of proving something to begin with. They have a very pragmatic approach where they say, well, if it works, that's all the proof you ever need. But I'm here to say that if you reprove something, it gives you insights that you wouldn't have had otherwise. Now, in order to demonstrate this, it's much more important that I get to the end of this process and actually start discovering new physics. And so to do that, I'll be making certain skips. On the downside, that's going to make the whole development of these inductions less rigorous, but it's much more important to actually achieve the goal of revolutionizing physics than it is to have a perfect induction. And again, the reason is because people are not going to care about induction until it has some kind of result. Now, as we proceed forward, I want to tell you what standards we will be applying as we skip things, because we can't just skip things willy-nilly. And once things are skipped, I want you to still understand what the inductive method is, because it can be a little bit tough to understand what inductive rigor is if I'm not completely achieving it. But I still want to indicate what inductive rigor looks like, even though I won't be achieving it. And I'll be able to indicate that by pointing out the holes and pointing out the sense in which they are holes. So here are the minimum standards that our inductions must meet. So first of all, the overall order of inductive development of these videos has to be clear enough to demonstrate the general principle of logical order. If there's too many holes, then you won't get a sense of what the whole journey looks like. So there needs to be a small enough holes, and the holes need to be minor enough so that you can still understand the general inductive progression. And in the case of skipping decimals, for example, it's hardly, I don't think it hurts us, because you understand, okay, well, we develop fractions, and decimals is some kind of combination of thinking in base 10 plus thinking about fractions. So you can roughly hold that in mind and understand how that leads us to the next step. Now, further, another minimum requirement for our inductions is that we have to develop the full context required to overhaul quantum mechanics and general relativity. we're not going to be skipping steps when it comes to these later steps that really form the foundation of quantum mechanics and general relativity. Now, the kinds of things that I'm going to tell you about the kinds of things that will be skipped and how the holes will be indicated or filled. Okay, so here's how that's going to work. First, certain steps that are going to be skipped. Steps that are easy, uninteresting, and likely free of error will be given a number in the inductive outline and simply skipped. So you'll notice that everything has been given a number, like they've been U 1.21 or something like that. If you ever notice a skip in the inductive videos, it's because that appears in the outline and it's not going to get its own video. So the classic example of this is decimals. That's going to appear in the outline as a number, but we'll be skipping those numbers in the video in order to get through the inductions faster. Units consisting mainly of mathematical deductions will be motivated, given a number, and then instead of going through that and making a video, I'm just going to cite where it appears in a standard math or physics textbook. So an example of this would be the differentiation algorithms. So how would that work? So what I mean by differentiation algorithms is certain shortcuts in taking derivatives. So like the power rule, the chain rule, the quotient rule, the product rule. These are shortcuts people have used in order to do derivatives faster, basically. And so when we get to a step like that, what are we going to do? We're going to indicate the need for something like that, probably prove the power rule, and then say, to prove the rest of these, just look at a math or physics textbook. So that's hardly even a hole in the narrative because it's filled by simply like looking at the rest of these. Further, something like differential equations, the subject matter is going to be introduced with a certain example, so it will be fully motivated. That example will be worked out, maybe a solution to some easy differential equation, and then it will simply be left as open-ended. Hey, read this textbook, and that will indicate how to solve an entire class of differential equations. Ideally, we would go through these details, motivating every single different kind of solution to every single different kind of differential equation. But as stated, that is not conducive to the priority goals of this project. Now, some units might be skipped altogether. In such cases, we may have to go back to those and develop them later. And examples of these might be the moment of inertia tensor, which is a very complex esoteric topic that specifically allows you to solve for very specific cases of rotational motion. I'm not sure if that's going to help us with quantum mechanics and general relativity in the long run. It might or it might not, so I don't want to cover it at first because it's going to take time. Another example would be the electromagnetic vector potential, although that's probably going to be useful. But we'll develop it when we need it to understand the ether on a deeper level. Because just to understand electromagnetism, you don't need that in order to understand the essence of electromagnetism. Let me also give you a sense of the kinds of things I'm not going to skip. So units that are easy but highly essential for the overall story. So for example, the discovery of the electric and magnetic forces. So, holding electric objects together and seeing that they repel. That stuff is easy, and you could argue it could be skipped because there aren't mistakes in that part of the literature, and it's easy, but it's just too essential. The story won't make sense if I skip things like that. Further, I'm not going to skip anything related to quantum or relativistic phenomena because that's exactly the point of all of this, is to recheck all of that. But I'm also not going to skip any of the concepts that were used in the discovery of those phenomena. So for example, Planck used a lot of specifics of thermodynamics in order to first hypothesize that energy was quantized. We're going to need to fully induce those specifics. So in general, the stuff that comes at the end is just not going to be skipped. Now, what are the costs of this decision? One of the downsides is that this video series is no longer going to constitute a rigorous inductive proof. To be rigorous, you truly have to cover everything, and I wanted to be straightforward with you about this. It's no longer a rigorous process. Now, there's also not just a cost here, but a risk. The risk is that any mistakes that are hiding in these skipped inductions are simply going to be missed. So if I skip a certain part and don't inductively prove it, and that part of the literature is mistaken or not well understood in some particular way, at least not well understood by me, I'm missing out on the inductive benefits when it comes to those particular subject matters. This is why I'm not going to skip anything that I either don't fully understand or I suspect is flawed. That's another kind of thing I'm not going to skip. So a full rigorous inductive proof of all of math and physics is just going to have to wait for later. This is a lot of work for one man to do, and I'm going to demonstrate the value of induction to get more people on board with the project before trying to complete the whole project of making everything 100% rigorous. All we need to do is just make sure that we gain the rigor necessary to reform physics. That is the primary goal. So I wanted to tell you guys this, so you understand the nature of the inductions going forward, that they will not be fully rigorous, but they will still generally show you how rigorous inductive proofs are done, and they will form that foundation to overhaul general relativity and quantum mechanics. So thank you for continuing to join me on this inductive journey.